Hi students, in this lecture I am going to discuss previous year's IIT questions based on self-induction and mutual induction. Let us see first one. A small square loop of wire of side length L is placed inside a large square loop of wire of side length capital, and condition is capital is very large compared to smaller. The loops are coplanar and the centers coincide. The mutual inductance of the system is proportional. Let us see how to start. So first of all, make a diagram for given data having two square loops. This is outer one. Let me take a current I flows in this one, or take it as I1 current is flowing. I am taking this as coil 1, current is I. Now I want to calculate. So taking here a smaller one here. To calculate coefficient of mutual induction, first we have to focus on flux linked with second coil, and that is equal to M into I1, right? So first calculate now it is flux linked with the second coil. So now what I am doing here is join the ends of the wire like this. Calculate now at this point what is magnetic field. If you remember, we made this calculation in the earlier chapter, right? That is what we call by using Biot-Savart's law. And see result what we got in that. At center field equal to it is a 2 root 2 mu naught I upon pi L. So this is the result we got, right? While discussing because of a square loop at center, what is strength of the magnetic field by using Biot-Savart's law, right? Now I am using that result directly here. Then see flux linked with this one. And you can see condition given. L is very large compared to small. See the purpose of this condition. When this is very small, means its area also very small. In this entire area, field will be uniform. Therefore, I can write flux phi 2 is equal to directly B1 into area, that is L square. And this is now B1. So this is equal to M into I, or it is I1, this is I. See from this what we can write. M is a proportional to in the place of B1. Write this value. I can say here proportional to L square upon L. Right? So like this we can get the answer. And we can see the question carefully. It is given that the mutual inductance of the system, right? It is not mentioned that in which coil current is flowing. So we have to understand that this M is not depending on in which coil current is flowing. So here we have taken current flowing in outer one and flux linked to the inner one, because this calculation is very simple. Okay. Or the same thing we can solve like current flowing in inner one, then calculating flux linked with outer one. Then what happens is we write phi 1 is equal to M into I2. In this case also, we get same M value, but calculation of flux becomes very difficult. That's why we have chosen current is flowing in outer one and a calculation of flux with the inner one. Okay, this is what we can say by using the principle of, or you can say this is known as reciprocity theorem. That says that, see what I can write here, number of turns in outer one, that is first coil N1. So total flux linked N1 into phi1, where phi1 is flux linked with each coil, okay, into number of turns upon L2, sorry, upon I2. This gives us coefficient of a mutual induction. And same thing we can get by using N2 phi 2. This is a flux linked with the second coil upon I1. And this is giving us again same M bar. Okay. Now multiply these two. We are going to get M square. M square equal to N1 phi 1 upon I2, N2 phi 2 upon I1. And you can see N1 phi 1 upon I1, that is a coefficient of self-induction. N2 phi 2 upon I, that is a coefficient of self-induction for second coil. That means M square is equal to L1 into L. That means M value root of L1 L. Okay. In fact, this depends on the orientation of the coils. Right. Let us see the next question. Let's see the question given. Two circular coils can be arranged in any of the three situations shown in figure. Their mutual inductance will be. So just now we have seen that M equal to root L1 L2, and in that we have discussed that depends on the orientation of the coils. Now see carefully. Here both are in same plane, means the planes are parallel, right? So here flux linked with this one will be maximum. And if you see here, flux linked will be minimum, or we can say it is 0. See carefully. When we calculate flux, it is B bar dot A bar. If I am taking current in this one, field will be upwards or inwards. And for this one, if I am taking area vector, normal, that will be either like this, right side, or it is left side. So in this case, between B bar and A bar, angle is 90. So here flux will be 0. And here between B bar may be upwards or maybe downwards. A bar may be up or maybe down. That means in this flux is means their mutual inductance. It is more because more flux is linked. Okay. And coming to here, this is non-zero, but definitely less than this one, because in this both planes are parallel. Okay, that means option is, it is safe, right? Let us see next one. The network shown in figure is part of a complete circuit if at a certain instant the current is 5 ampere and is decreasing at a rate of 10 power 3 ampere per second, then VB minus VA is, right? Let us see how to start. Right, first of all, see the given circuit. So having a resistor. So taking a battery, then inductor, So this is A and this is B, and see the current given. Current given is a 5 ampere. I is a 5 ampere. And one more thing is condition given that current is now decreasing, and that at what rate current is now decreasing, that is given as di by dt, that is 10 power 3. I conduct minus 10 power 3 ampere per second. And coming to inductance given 5 millihenry, right? And this is 1 ohm, and this is 15 volt. And we have to calculate VB minus V, right? And see what we have discussed earlier. So first thing, we have to replace inductor with an equivalent battery, right? So first thing, current flows right side, and current is now decreasing. Therefore, we have to replace now this with a battery, and that should be like this. Because current is decreasing, it tries to oppose the change. Therefore, it tries to increase the current. Okay. Right. Now take Kirchhoff's second law, starting from here. At that point, potential V A. Now moving along the current flow. Along the current flow means it is now minus I into R, I value 1 into R, that is 1. Next. Now it is low potential to high potential. So plus 15, right? Next. Now again from low potential to high potential. And this value how much means? This value L into L is 5 10 power minus 3 minus di by dt. Okay. Di by dt minus 10 power 3. It is now minus di by dt. That is a 10 power 3. And that will be equal to 5. So low potential to high potential. It is now plus 5. That is equal to VB. Right? Then see what we get. VB minus VA. That is equal to VB minus. So taking this one to right side. So minus 5 plus 5. These two cancel. Remaining is now 15. Right? Like this, by replacing inductor with an equivalent battery, we can simplify the circuit. Let us see next one. Right, see the question given. A circular wire loop of radius r is placed in the xy plane centered at the origin O. A square loop of side A, condition A is very small compared to R, having two turns is placed with its center at z equal to root 3r along the axis of the circular wire loop as shown. The plane of the square loop makes an angle of 45 degrees with respect to the z-axis. If the mutual inductance between the loops is given by, then the value of P is, okay, right. See how to start. So whenever you want to calculate coefficient of mutual induction or coefficient of self-induction, first we have to focus calculation of flux. And we are knowing that on the axis of a circular coil, magnetic field equal to, it is a mu naught NIR square upon 2 into R square plus X square whole power 3 by 2. Okay. Now in this case, given distance is root 3r. So take x value root 3r. X value root 3r. Then see what is b value. And number of turns not mentioned here. So we are taking that as 1. Right? So mu naught n is 1. I value I only r square upon 2 into this is now root 3 whole square. So 3r square. 3r square plus r square. It is 4r square. 4r square whole power 3 by 2. That becomes, so that becomes how much? Let me see once. It is now 4r square. 4r square means I can take it as 2r whole square. And here 3 by 2. So 2r whole cube. That becomes now 8r cube. Right? R square, and this is gets cancelled here. Remaining is now, this is a field. Now coming to flux. Flux equal to B into A. Mu naught I by, it is 2 into 8R into A value. See how much A value? It is A square, right? A value. And number of turns given 2. So into 2. And 2 to cancel here. And see what else left. And you are given here between that coil and z-axis angle 45 into cos 45, because this is now b bar dot a bar, b into a into cos of the angle into 1 by root. So this is now equal to mu naught I a square upon, this is r, this I can take it as 2 power 3, this is 2 power 1 by 2. This becomes now 2 power 7 by 2. That implies Cp value. It is 7. Okay. Because this is pi equal to m into y, right? M into y. I cancels. Right? Okay, let us see the next problem. Let's see what is given. The conducting loop in the shape of a right-angled isosceles triangle of height 10 centimeter is kept such that the 90-degree vertex is very close to an infinitely long conducting wire as shown. The wire is electrically insulated from the loop. The hypotenuse of the triangle is parallel to the wire. The current in the triangular loop is in the counterclockwise direction and increased at a constant rate of 10 ampere per second. Which of the following statements are true? Let us see. This is now given that, and options are given. Magnitude of induced EMF that we have to calculate. And next, if the loop is rotated at a constant angular speed, first focus how to start the problem. So make the given diagram. So having here long wire, and taking here one triangular loop, it is isosceles. It is given almost touching and given isosceles. Isosceles, and angle is given 90 here. And this height is given as 10 centimeter. Right. So first calculate here the magnitude of induced EMF in the wire is. magnitude of induced EMF. And coming to the question, see what else mentioned here. It is mentioned that the current in the triangular loop is counterclockwise and increased at a constant rate of 10 ampere per second. So in this current is now counterclockwise. Current is counterclockwise. And this current is now increased at a constant rate of 10 ampere per second. So di by dt, that is given as 10 ampere per second. Right. Coming to first option, magnitude of induced EMF in the wire is. So here what we are doing is, now we are going to use reciprocity theorem. Okay. That means we assume that current is flowing in this long wire and calculate flux that is through this loop. Then differentiate that, we are going to get EMF induced. Okay. Let us see now. Assume that at a distance x, take now one rectangle, its width equal to dx. This width is now dx. Okay. Then see, at a distance x, field because of this current carrying wire. Okay. That I am taking as current as y, so current as I. So taking this current as I and assume that is now changing at the rate of 10 ampere per second. Then see what happens. See here why I have taken current direction is right side. We are given that in the question. We can see in the question it is mentioned the current in the triangular loop is counterclockwise. Okay. And one more thing given, current is increasing. You see what happens. Current increasing. Here current increasing. Therefore, flux will increase. Right? Counterclockwise. So counterclockwise means keep the thumb, or I can say curl fingers of your right hand counterclockwise. Then thumb will be towards us. That means in this location, direction of field because of this current is towards us. Then direction of induced current in this long wire must be in such a way that because of that wire, field must be inwards in this location, right? That's why I have taken direction of current is right side. Okay. But now what we have been using reciprocity theorem, assume that current flowing in long wire, calculate flux linked with this triangular loop. Right. Coming to B value. Integration of, because of this one through this loop. Sorry, not this big flux, right? I am calculating flux here. Flux equal to integration of mu naught I by 2 pi x, that is B into this area. This area how much? See carefully. If I am taking like this, since angle is 90, this is a 45, this also 40. When this is x, this also x, opposite side. Then this also x. Therefore, length is 2x. 2x into dx. That is now area of that rectangle into B. That is a flux. Like this, take all rectangles from x equal to 0 to x equal to 10. Okay. X equal to 0 to x equal to 10. See what we are going to get. 2 to x gets cancelled. Mu naught I upon pi into integration of dx. It becomes x, right? And that X value how much? 10 centimeter. This is a flux. But we have to calculate EMF induced. That is given by, I am focusing only modulus value. So d phi by dt, not taking a negative sign. So mu naught by pi 10 centimeter into di by dt. That is now 10. So 10, 10, 100. This is a 10 power minus 2. So finally value is now mu naught upon pi, right? That is now EMF induced. So option A is correct, right? Next. Now see the next option. If the loop is rotated at a constant angular speed about the wire, an additional EMF is induced. If you see carefully, this is a long wire, okay? Around this wire, if I am taking at any distance x, let me take like this. I am taking up this long wire like this. If I imagine a cylinder of radius how much? 10 centimeter. Now this loop is rotating about this axis within that cylinder. And you can see there is no change in the flux through this loop, because if I am taking field at this location or field at this location, both will be same. So because of that symmetry, there is no change in the flux. That's why no additional EMF is induced. So I hope you got a clarity, because this is a long wire. Field lines are concentric circles. So when this is rotating, flux through this loop is not changing. Okay, right. Next focus. The induced current in the wire is in opposite direction to the current along the hypotenuse. Along the hypotenuse. You can see this is the right side and this is also right side. That means it is not correct. Okay. Next. Coming to fourth option. There is a repulsive force between the wire and the loop. Then see what happens. How to verify this option. So I think we can verify this option like this. In this area, flux is now increased, right? In this area, flux is increased. So when you are taking current flowing like this, and this current is increasing, so flux value will increase here. So to decrease this flux, or you can say direction of induced current is in such a way that it opposes cause of its production. Okay, then there must be repulsion between these two. When there is repulsion, what happens is, if it is moved away from this triangle like this, at this location, strength of the field will decrease. Get the point? If you see, for example, we have attractive force, then what happens is, in this location, strength of the field will increase. So flux increases. But here, EMF is induced because of increase in flux. Therefore, it tries to decrease it. So trying to decrease, the only possibility is this loop has to repel this wire. Then strength of the field can decrease. That's why it must be repulsion. Okay. So I hope you got a clarity.